Hello, today I'm gonna be talking about generating physically realistic footwear contact pressure distributions with diffusion models. And first, we declare no conflicts of interest. And the main reason why we care is because generative AI is now part of the design loop at major footwear brands. And this can be reflected in companies like Hoka or Nike. But the key question is if generative AI can also be used to do research. And I assume that most of you are already familiar with diffusion models, but just know that these are really powerful image and video generation models, capable of achieving generations like this. And although the outputs of these look extremely realistic, the key question is if these models can generate physically realistic outputs that we can use for different biomechanics applications. And our vision is a feature of footwear design powered by generative AI. The idea is that we can start with a shoe sketch or a shoe image, and then for a set of force and shoe angles, we can compute the pressure distributions, and that would fit a shoe optimization step that would then update the shoe design. But in practice, we found that this was much harder to do, so we had to introduce a couple of steps. Namely, we first had to predict the full contact and then the partial contact. And so in this presentation, I will first talk about contact pressure distributions, then about diffusion models, and finally about physics-based diffusion models. And you may wonder, so why do we actually care about contact pressures? Well, contact pressures are relevant in two settings. We know that in the workplace, slips account for 42% of the total non-fatal injuries. And then also that in sports, too much traction can lead to injuries. And the key modifiable factor is footwear friction. And a factor that governs that friction are the actual contact pressures. And the way that we can get contact pressures are by using a technology which is called frustrated total internal reflection, or FTIR technology. And so here I will show you a video where on the right you will see someone stepping on a plate with FTIR technology, and then on the left you will be able to see the pressure distributions as the person is stepping on the plate. And so I'm going to play it one time. I'm going to leave it another time. And I'm not going to get into too many details, but just know that the idea of how this technology works is that we have a plate, which is surrounded by LEDs, and then the light emitted by the LEDs gets internally trapped inside the plate. But then when a shoe thread gets in contact, then that light gets redirected out. And if we take a picture, we can get an image that looks like this for a particular thread design. And then to convert this image, or I guess the pixels intensities, into actual pressures, we can do so by using this equation. And this is something that we're currently working on. And for those of you that are not that familiar with diffusion models, just know that these are generative models that they essentially learn to denoise. So the idea is that we have what is called the fixed forward diffusion process, in which we start with our raw image or our clean image, and then at different time steps we add noise until we end up with completely random noise. And this is not learned. What is actually learned is the reverse process. And so typically, the network that learns how to remove the noise is called a unit. And so now, going back to our vision, I will first focus on the step of going from the partial contact into the pressure distribution. And so for this, so the model inputs were a force and then also partial contact. The model outputs were the pressure distribution. And for this, we had a setup of 10 shoes, and in total, 700 frames of data. So around 70 frames of data per shoe, more or less. And what we did is that we fine-tuned control net with low rank adaptation. So the idea is that we have a unit that has already been pre-trained, and so we keep the base model weights frozen, but then we add some adapters on top, and that's what we actually train. But so far, you may have realized that I haven't said anything about physics, and so if we have our AI friend here that wants to generate physically realistic pressure distributions, it needs to understand physics, right? So how can we let it learn physics? Well, so the intuition is that we inject force as a global input that the whole network can condition on. So here you can see a slightly more detailed schematic of the base network. Here you can see how time step was added to the network. And here you can see the low rank adapters added to all the attention blocks. And so if we have a biomechanical input, in this case force, we just inject it the same way as how time step was originally added to the network, in particular to all the ResNet blocks of the unit. But then, in addition to doing this, there are a few tricks that you need to perform. So for example, you first need to normalize the pressure distributions to be in the range of -1 to 1. You also need to repeat the normalized pressure channels. You also need to initialize the physics conditioning weights to 0. And then during generation or during inference, we perform what we call a force projection step. So the idea is that here f hat essentially denotes the computed pressures from the predicted pressure map. So essentially, by summing all the pressures times the area of all the pixels, then we come up with this coefficient in which F applied is the ground truth force applied, and then we just use this coefficient to scale all the pressures to ensure that their sum is equal to the known force. And then the last trick, which is extremely important, is that you need to play, so that all this will work. And so now getting into some results. So we did a leave one shoe out cross-validation, and across 10 folds, we obtained an average pressure error of 5%. And so the idea is that once the model is trained, the model will start with a completely random pressure distribution, and then it will keep taking denoising steps until it converges to a physically realistic pressure distribution, as can be seen in the animation right here. And I'm gonna let it play one more time again. And so that's pretty cool. But then going back to our project, so I will now talk about the prior step. And so the step will be going from the full contact into the partial contact. And so for this, so the model inputs were a full contact, a force, and 3 shoe global angles, and then the output was a partial contact. For this, we had a similar setup, so 10 shoes, and in total 700 frames of data, and we also fine-tuned control net with low rank adaptation. So that's kind of like the same idea. But then here, so you may see that we not only have one biomechanical input, so we have 4. So how do we go about injecting them all into the base network? Well, so here you can see the same schematic as I showed you before. And here you can see the 4 biomechanical inputs. And note that the shape of every input is batch size. So the first step that we do is that we concatenate all of them into a single longer tensor, which is batch size times 4, and 4 for 4 biomechanical inputs. Then we feed this into the shared sinusoidal positional embedding, and then we just use the same MLP, and we feed all this into every single resonant block of the network. And getting into some results. So we did a leave one shoe out cross validation, and across 10 folds, we obtained an average DAISY score of 0.6. So here you can see an input image for a shoe, which would be the conditioning image. Here you can see the ground truth contact, so the contact that remains for a set of force and 3 shoe global angles, and here the predicted. And this would be for one shoe, and then for another shoe, here you can see also the input, the ground truth contact, and finally the predicted. And so as take-home messages, so first, physics conditioned, latent diffusion models can generate physically realistic contact pressure distributions from minimal inputs. And so now our AI friend here is happy because it understands physics. Also, secondly, once this is ready, designers could get instant pressure feedback on every design decision. And the final take-home message, which is extremely important, is that if you develop a technology, you shouldn't try to immediately replace it with AI. I would like to thank everyone that helped with this presentation and then also with this research. And yeah, thanks.